welcome to another episode of Introduction to Computer Networks. Good morning, all. So, good morning, Yuxuan. Today, we're just gonna go ahead and start because there's nothing more to announce. And we have one more video about delay we're yet to see. It's about how you measure delay really on the internet. So here's the video.
All right. So that was the theory part of the packet delay. One can also find out what is the real internet packet delay by trying out this program, traceroute. Okay. What it does is to measure delay from a source one hop at a time all the way to a destination. So this is what I'm drawing here, source to destination, and it's sending 3 packets one at a time to reach each of the routers along the way. So router there receiving such a packet would return by sending a reply back to the sender. Now the sender there can time the interval between the transmission and receiving the reply and gets one estimation of the round trip time between the sender to the router. So it works like this: 3 probes to the first router, 3 round trip time estimation. 3 probes to the second router, 3 round trip time estimations to the second router. And this goes on and on until it reaches the final destination, and then the traceroute program stops. The output of the program looks like this. This is an example. Trace routing from Gaia.umass.edu to Oracom France. So this is saying first hop router's name is cs-gw at IP address 128.something.something.something. And there are 3 round trip time estimations, 1 and 2 milliseconds respectively. What's a little bit interesting is between hop 7 and 8. There. You see at hop 7, round trip time was about 22 milliseconds, but suddenly to hop 8, the delay is about 100 milliseconds. So that is the transatlantic links connecting from US to Europe. A little bit more interesting is also hop 17 and 18. You see stars. That means the routers are not responding. Okay, and it could be because the probing messages are lost or the replying messages are lost. But it's more likely that the router is turned off replying to these. Routers are on, but the routers turn off replying these probing messages. Well, let's try, sending a trace route ourselves from here. How about that? Go over to a terminal and then trace route to say Google. How about that? All right. Good. First hop router. Well, it didn't tell me the name of the router, so chances high that the router doesn't have a name. Okay. Delay reasonable. 10 millisecond, 3 millisecond, and another 3 millisecond. Router 2 here, well, either the probing messages are lost or router turns off the functionality of returning to traceroute probes. Now third hop, 30 milliseconds, suddenly much higher. Okay, fifth hop, delay not much higher than the third hop. And you see here, when it's star, it takes longer time. It's because when the traceroute program sends the probing packet, there's a timeout interval. Traceroute will wait until the time exceeds the interval. Then it determines that, hey, the router is probably not going to respond anymore. So forget about the first probe, send the next probe. Next probe waits also some amount of time. Timeout, give up, and then sends the third probe. Okay, good. Finally, we reached www.google.com. But the name is actually quite different. TSA something. Interesting. And the end-to-end delay, end-to-end round trip delay to www.google.com is about 20-something milliseconds. Now, something that's very odd is here. Hop 8. If you look closer, we do have 3 round trip time estimates. But each time, number A here along the way, the 8th hop, is slightly different. IP address is 101, 49, and 97. So you see here, packets, although going to the same destination, coming from the same source, as they go on the internet, the routes could actually change. Also, you see, hey, the time it takes to reach hop 5, 30 milliseconds, but the time it takes to reach hop 12 is only 20 something seconds. So the load of the internet changes also over time. So sometimes when you are probing to a closer router, could take a longer time because it was busier there. But when the traffic load drops and when you're probing a router that are farther away, you could get a shorter round trip delay. Yeah, very curious. And let's go back to the slide. And it turned out that it's a good time to start the next quiz.
And here's quiz 6. Okay, Tanya was asking about it yesterday. So here's the quiz 6. You know what? This is the output that I showed in the video, the trace route from one location to www.yourcom.fr. Okay, and I'll come to the questions. Very good. You guys are getting used to the lecture mode and picking up the content in the video. That's how you are able to ask questions. But let me finish the quizzes and then I'll attend to the questions. Oh, some of you are very smart. Yes, W3 Quiz 6 channel, the quiz is posted. Okay, feel free to try and join the channel. So, quiz 6. Essentially, I'm asking you to examine this measurement output from trace route a little bit closer. Okay, and if you pay attention to that video that I just played, you should be able to answer Q1. How come the 3 delay measurements to the same hop, same router, they are not quite the same? How come? Q2. This you should be able to answer as well if you pay attention to the video. How come sometimes delay measurements to a hop that's closer, for example, hop 10. If you read the row says 10, the 3 measurements are 113, 121, and 114. But if you read the 3 measurements to hop 11, that row says 11, 111, 114, 112, 114, and 112. Hey, the average delay to the 11th hop seems to be shorter, right, than the 10th hop. How can this be happening? Why? Now, Q3 is a little bit more advanced. Given a measurement like this, can you estimate the delay between hop 3 and hop 4? Okay. If you, again, pay attention to the video, you see that trace route is sending what? 1 probe, 2 probe, 3 probe for each of the hops along the way to the target you're trace routing. So there are 3 measurements at the time, and that delay is go and back. That's called a round trip delay. And what I'm asking here is the delay from hop 3 to hop 4. That's one-way delay. Okay, can you estimate the one-way delay between hop 3 to hop 4? And can you estimate the delay from hop 8 to hop 9, just between those 2 hops? Now, give me your estimated delay and tell also how you come to the estimate. Okay, good. Now, let's start working on it. You have 8 minutes to work on this. This is now 10:29. You have it until 37. Okay, let's go ahead and start. Yeah, Claudia, good morning. Yeah, you're the first to answer this morning. So the answer for Q1, the 3 delay measurements are not the same because there are two different reasons, right? Because if you recall, delay has 4 components. There are 3 components that are either negligible or easy to compute and more or less constant. But queuing delay can vary, right, depending on the other traffic interworking with the probing messages you're sending. Yeah, so that queuing delay can go long or short from time to time. And your 3 probes are going into the router at different times. Therefore, yeah, the delay can be different, of course. Very clear. Number 2, you know what? In different probes, the route that you're sending the probes might not exactly be the same. As you see in the video, right, Polly tried to do a real trace route from her machine. And in one of the hubs, right, we're seeing 3 different routers for 3 different probes. So the routes themselves for 3 different probes can in fact be different. Even though the destination is the same. Very good. So these are the 2 main reasons that you see the measurements are not quite the same. Okay. And I guess, yeah, Q2. I think Claudia is probably struggling a little bit with formatting your answer on Slack. Hey, you'll get better. Oh, there you are. There you are. Yeah. The packets returning back to the source, the timing may be different at the first packet sent to the hop 11. And when at the time that the source sends the 3 probes to hop 10, there might be some more congestion, of course. Yeah, the same reason that the 3 delay measurements are not quite the same. And it could happen that a few seconds ago when you're probing hop number 10, hey, queuing delay is just high. And then suddenly the background traffic goes away, connecting to hop 11 faster, isn't it? And of course, one can also argue that the routes, when the probes are going to hop 11, might be slightly different. Somehow the delay is shorter. So for Q1 and Q2, I believe that if you just follow the video, you know the answer for them. Now, for Q3, it's a little bit tricky, isn't it? I guess that for many of the teams, you guys need to ponder a little bit more is for Q3. Let's see. Zhen En speaking on behalf of Team 15. Okay, guys, observe. I think that each of you have your own answer, and you discuss with your teammates, and you might discover, hey, that is a better way of thinking that's a little bit more thoughtful than yours. And let's now see other teams' solution to estimate delay between hop 3 and hop 4. So let's see, Team 15. The delay between hop 3 and hop 4. What did they? Oh, okay. Yeah, so there are more answers being typed up, so I lost my screen there. Let's see. Interesting. Okay, so I think Team 4 is doing this, adding the delays to hop 4 together. Wait a minute. Very interesting. 16, 11, subtracting 13. What is 13? So maybe you can go back up here. What are the 3 measurements to hop 3? 16, 11, 13. And hop 3, 6, 5, 5. Interesting. So team 15 is adding 2 of the measurements and subtracting 13. Interesting. I think that's a way of calculating the sum or average, isn't it? Yeah, so that removes the need of a divider. You can add the 3 numbers and divide it by 3, but subtraction and addition is they are easier to do. Okay, very clever here, Zhenan. And 655, yeah, the same way of doing the calculation. Ooh, cool. So, and you divide it by 3, but wouldn't that be too low, right? If you have already the average, isn't it? Yeah, let me know, Zheng'en, if you agree with me. You probably don't need dividing the number by 3 again. But you do need to divide it by 2, so you get just one way, isn't it? Okay, I guess you do the same for hub 8 to 9. Interesting. Very interesting. So I guess the general approach that Team 15 is proposing is just calculate the average delay to the later hop, average delay to the earlier hop, subtract, and then divide it by 2. Let's see if we get the same thing. Oh, interesting. Team A here, for the delay between hop 3 and hop 4, Naiming came up with something very similar to Zheng'en. But for the delay between hop 8 and 9, it's too small to estimate only by 3 probes. But generally, you do the average delay difference divided by 2. But I guess hop 10 and hop, I mean, we just ask about hop 10, hop 11, isn't it? Or no? So sometimes you get a delay to a later hop being shorter then how do you estimate the delay between the 2 hops? That's odd, isn't it? I think there's a similar situation between hop 8 and 9. Yeah, I think the average to hop 8 is higher and to hop 9 lower. But I guess what Zheng'en was doing is probably subtracting the middle value, right, of the 3 measurements. I think that's another way. Instead of doing average, you take the middle value. Yeah, median is an alternative way to estimate, for a sample of numbers, right? 2 samples of numbers. Median is a way to characterize also the middle point of the sample. Okay, I guess this is what Zheng'en meant to say is median. To hop 8 and median to hop 9 and divided by 2. Okay, got it. So earlier we use average, but later use median because the 3 values are a little bit weird, as Naiming pointed it out. Okay, very good. All right. Let's see 13, 右翔 on average. I see. Okay. Divided by 2. Okay. Between port 8 and 9. Yeah, Zheng'en, I think yeah, you need to divide by 3 as well. Yeah. It's more difficult because it's just the sum. Estimate since probing time is almost the same. The delay is subject to the traffic condition. Yeah, between port 8 and port 9, team 13 is also a little bit reserved to use just these three numbers. Yeah, so you probably would try to measure a longer time or something like that. Take more measurements. Yeah. Okay, team 7, half 3 to half 4. Oh, okay, without subtracting the earlier, the delays to the earlier hops. But I think this is more the one-way delay to half 4, isn't it? Yeah, I think similarly, this is more the one-way delay to half 9 as well. Okay, think about it. Take the average. Okay. Yeah, so team 6, hey, whatever, just take the average. Yeah, that's one way. Now, whether it's a more thoughtful, careful way, that's, of course, another issue, right? Yeah, so Zijun just take the average. All right, that's one way. Xuan is getting a negative delay. Yeah. Okay. Okay, so team 3 also use the average delay. Yeah. And team 11. Interesting. Yeah. Good. Very good. Very good. So for Q3, I guess some of you would rather be a little bit more careful and say, I'm not sure if I just take the average is okay. But others say that, hey, from the data I have, that's the best I can do. Okay, good. So yeah, I think you guys all get the idea. So those measurements are not being done exactly at the same time. So there could be longer, shorter. And for the question at the end of the video, Hongru asked if router 2 is dead, right? Then usually the probes won't reach half 3 and so on and so forth. Exactly. If the router is dead, then no, definitely. And in that case, more often you probably find that there's another route to send the probing messages. So Zhongmin was helping, trying to answer. Router 2 there might be just turning off replying to the trace route probes. Okay, that is very often the case. Yes. Okay. You see that these asterisk signs, if there are only one of them out of 3, then just the packet loss. Now, if you see all 3 probes showing asterisk sign, that means usually that router turned off replying to trace route probes. Good, and now we can start talking about the 2 other metrics. Okay, and they are loss and throughput. Loss is very straightforward. Packet loss is a lot more straightforward. You see, it's because the queue is finite in capacity. So in case the packet arrives when the queue there in the router is already full. So you see this full packet here, will need to be dropped. That's why we see packet losses. Now, what we haven't discussed is this, the lost packets. To some application, it's actually okay to have packet losses. If it happened, let it happen. So we will not try to retransmit the packet at all. But in some cases, for some applications, users are expecting the messages arrive fully intact. Then we might need to retransmit. Now, as to which entity in the internet to try to do the retransmission, it's really up to the design. So in some cases, we might see the previous routers doing the retransmission. But in most of the cases, we see the original source, the source end system is doing the retransmission. All right, so loss, very simple. Throughput, slightly more complicated. Throughput is the third metric. And it measures this thing, the rate of transmitting data all the way from the sender to the receiver, from one end to the other end. And the speed of data is going through the entire channel, entire pipeline. Now, there are two ways of quantifying throughput. One is called the instantaneous throughput, the other, average throughput. Now, the units are both bits per second. Okay. But instantaneous throughput is more that you're measuring the throughput at a particular point in time. You will see that if you measure instantaneous throughput, it will fluctuate depending on the situation of the channel between the source and destination. But if you observe over a longer period of time, then you see that the average throughput is more or less stable. Okay, so the throughput here we're talking about and discussed throughout the rest of the sites will be more the steady state behavior, the stable average throughput, just to clarify. Now let me elaborate the example a little bit more. This is the sender, this is the receiver. The sender is essentially a file server hosting big files here. Let's say the file of f bits is being sent over to the client requesting the file. And so we're talking about just the file download, okay, not the request part. And connecting the server and the client, we have one link, one switch, and another link. So it's a two-hop network. And the link capacity for the link directly adjacent to the server is RS, and S here indicates it's the link to the server. And this guy here has the link capacity of RC, and C indicates this is the link rate for the link connecting to the client. Now, let's consider, okay, such a data pipeline as a fluid pipeline, water pipeline. Then you see, I'm drawing, okay, the pipeline's width, the diameter, based on the link capacity, RS. So RC here, let's assume it's larger, then you see a bigger pipe versus RS, smaller pipe. And you can also think about the server here being a what? Okay, a water tank, dumping waters, dumping fluid into the entire pipeline here. Now, it might be a little bit easier for you to imagine, right? What is going to be the pipeline's throughput if you consider how the fluids will be arriving at the receiver effectively? Would it be RC or RS? Well, it's probably not that hard, isn't it? Because the intuition tells you that, hey, this guy here, RS being smaller, will limit the amount of fluid that can travel through. Okay, even though RC is bigger, yeah, the amount of water that will go through here effectively to the receiver is still RS. If it's the other way around, RS being larger than RC, yeah, there could be a lot more water coming in, okay, overall carrying RS throughput, but this guy here being thinner is going to limit the rate of the fluids travel through. So in the end, at the receiver, okay, RC is going to be the throughput. And this guy here and this guy here, the link on the end-to-end path with the smallest bandwidth is going to constrain the eventual throughput. Okay, so throughput here oftentimes is being called the end-to-end throughput to indicate that it's the rate of data being sent from the source, one end, to receiver, the other end. Well, after drawing the data network to a fluid network, you see that it's very intuitive how you derive the throughput from one end to another end. And those scenarios are very straightforward, just two links. Let's consider a case that's a little bit more like the internet, okay? Deriving the throughput for an internet-like scenario. So you see here, we have servers and clients, okay? Data will be going from the servers down to the clients through the backbone, the internet backbone. So for each connection end-to-end, we'll be going through how many links? 1, 2, and 3. So we'll be taking the bottleneck link bandwidth as the throughput. So we'll be trying to get the minimum of the 3 segments. Okay, RC is this guy, RS is this guy, clear. The middle segment, well, if there are 10 links in parallel, then this middle link here, capacity R, will need to be divided by 10, as I'm assuming the 10 connections are fairly sharing the entire capacity. So the throughput to be formulated is this: minimum of RCRS and R over 10. In practice, however, okay, nowadays on the internet, usually it's either RS or RC being the bottleneck. You see, this is an N system, this is an N system. We subscribe access to the internet through some ISP. So this, usually the rate is low. Just like this, the application service provider, they are also subscribing to their ISP. This is also low. As opposed to the big R here in the middle of the internet, in the backbone, those are usually large. It's just that nowadays, there are a lot more connections sharing the big R. Okay? Most of the time, RC, RS are the bottlenecks. But occasionally, you might also see when network is really congested, R is not quite enough to allow all the connections demanding services. All right, so that's the last metric. Key point: the throughput is determined by the bottleneck link, the bandwidth of the bottleneck link. All right, so there was a question from Matt asking why the packet loss of ping and trace route being different. Okay, good question. If you recall, trace route does this: 3 probes to the first router, 3 probes to the second router, 3 probes to the third router. So what ping does is hey, you ping a destination, and that message just go ahead, reach the destination, and the delay coming back is exactly the round trip from you to the destination. So the routers in the middle are not responding to your probing messages if you do just ping. So you get just delay continuously. That is the delay to the destination. To trace route, you get 3 probes until all the way, and it will end. Okay, so packet loss in trace route, it will look like an asterisk, but packet loss in ping, it will look more like no packet. Okay, I'm not sure if you tried pinging a destination before. So it will be line, delay estimation, 1 line at a time, and then losing a line, or a line saying error, okay, and so on and so forth. Okay, so they look different, but when you see that and asterisk sign or error line in ping's result, they actually meant the same thing: packet loss. Okay, and every now and then you get packet loss on the internet because what? The queue might be full, so it get dropped somewhere. Or if there's like a wireless link in the middle, chances very high that it get lost also. Now we'll start another topic. So that was performance of the internet, how we measure the performance of the internet. Next, we'll talk about this notion, layered service model. Okay, so this is also called formally the internet's layered service model. Let me start with the opening video introducing what we'll be talking about in this section. 1.5, protocol layers and service models. Well, this is a very special section. There's not much really technical here, and the purpose is essentially to explain more. You'll see later in chapter 2, 3, 4, 5. The chapter's title is called something layer, something layer, something layer. We kind of talk about all these internet protocols or internet mechanisms by grouping them into layers. So chapter 2, we talk about protocols running in a particular layer. Chapter 3, another set of protocols running in yet another layer, and so on and so forth. So 1.5 here is to give you an idea why we kind of classify protocols into layers and what does each layer do in terms of functionality, making sure that the internet operates seamlessly. Okay, so we call that the service model, the internet's service model, or the architecture of how we organize softwares running on the internet. All right, so that was the overview. Let me go to the terms, okay, that we'll be using, okay, in the next 10-15 minutes. Now, let's recall all the terms we've referred to since the beginning. Right, we've seen hosts and systems. They're essentially the machines composing the edge of the internet. And then the core of the internet, right, the other one at the center of the internet being a mesh of interconnected routers. And then connecting the edge and the core, we do have these access networks or access links that operates different kinds of physical media running different kinds of modulation mechanisms. Yeah, access network. So these nuts and bolts compose and form the physical, okay, infrastructure of the internet. So this is more the hardware side of the internet. But we also talk about that, hey, hardware is not the only thing, okay, that makes the internet work magic today. A lot of times we rely on these applications in order to what? To see a page that we are looking information from. Okay? So applications such as World Wide Web email, and these applications a lot of times, right, it's implemented in a way that there's some part of the application running on one physical entity and then another part running on another physical entity. So if you recall, for World Wide Web, there's the client side on the client machine, and then there's the server, the web server running on the web server machine. Okay? And these are client and server side will need to communicate based on a specific rule. Okay? And so those rule forms a protocol. So there's also a protocol for the World Wide Web. Okay? So this is one example of the software on the internet. And there are a lot of these softwares. Okay? An application is just one kind of software, right? So in terms of software, okay, there are a lot more to talk about, a lot more pieces. In fact, the hardware part, and this is a very simplified view, okay, there are also a lot of other hardware pieces as well. In fact, to talk about a complex system like this, we do have a major question to begin with. Okay, is there a way, a hope to organize these pieces so that it's a little bit easier to teach or a little bit easier to discuss? Okay, not just between the senior network engineers, but also, okay, for the incoming network engineers, and how the senior ones teach the junior ones. Okay. All right, so that's why we say internet has a layered, okay, structure. We actually group the protocols, one layer, a group, one layer, another group. Okay, great. So next I'm gonna give you an example. Okay, not internet, another system, another communication system or transportation system that use also similar layered structure. Let me try to use an analogy, air travel here, to show you that it's kind of important to have some sort of organization, some sort of architecture, okay, to make sure a complex system will work seamlessly. And you will see also air travel and internet. Okay. Air travel to communicate people, internet to communicate data. They're somewhat similar, and therefore the architecture used by air travel is similar to the architecture used by the internet. Yeah, by architecture here, I meant the service model, the way the service operates. Good. Now, recall your experience traveling through air. First thing you do, purchase the ticket that guarantees you a seat. At the day of travel, you walk up to the counter, you present your passport and the ticket number. They will allow you to check in your bag and give you the boarding pass. With that, you go to the gate and they let you into the plane. And then the pilot will be negotiating with the traffic control of the departure airport and decide which runway and at what time the plane can take off. And then for a long time, you're just sitting in the cabin and try to get some sleep. But the pilot is busy doing this, okay, routing the airplane. Okay, so as the plane crossing border of some air control, communications will go on again and making sure that the planes traveling the air, the space, will not collide to each other. And hopefully everything is fine at the arriving airport. Again, pilot talks to the traffic control and find out the runway and the time to land. When the gate is connected and open, we may now leave the plane. Most of us go to the baggage claim to pick up our bag and exit the airport. So it looks like it's a series of steps. Very simple. But if you think about it a little bit more, right? Purchasing the ticket is important so that it guarantees you a ticket. So that when you go to the counter, when you're trying to check in your bag, they recognize you, right? And the base of the recognition is on the ticket number, okay? Acquired here and checked here. And in return, you get a bag number, which is used again here. You get also what? A C number, which is used again here. So there are still some communication that needs to be done, for example, between the steps, in between these two steps. Okay. So this component here, more closely related to this component. This component here is also more closely related to this component. And this component also connected and related to this component, even though this is at the departure airport, and this is at the arrival airport. Okay. So you see that there are components that are related, and there are some base in order to communicate between the staff members here and the staff members here. Okay, the mechanism here and the mechanism here. But you see also, for example, baggage check here. Well, it has less to do with the pilot communicating with the central control. Okay, you see also a little bit, right? This is a little bit more like the internet core. The functionality is quite different, but these are a little bit more like the edge of the internet, where you're trying to track data. Here we're trying to track passengers and the belonging of the passengers. Okay. And so that it's probably not that hard to see. There's a architecture there, okay, and it's kind of laid out in layers like this, right? This is communication to traffic control, but at the end, communication to air travel on the other end. Communication of air travel, but from region to region to region to another region's traffic control office. Okay. So to regional office, it's just to make sure that the height and the orientation of the travel is correct. Now these involves also runway. So you see there's slight differences between these two layers. Now these three are more handling the passengers and baggages, not handling the plane per se. Okay, so which gate we get in and which gate we're coming out. So your families and members will know where to go to pick you up, for example, to welcome you back, for example. And baggage here, the number is important. At the destination, you also want to know which station is for the baggage claim. There are usually multiple of them, right? So it's also based on the plane number, the flight number. Similarly, ticketing. Sometimes you need to delay travel, right? So you need to call the ticket office again to try to change the day or change the class, okay? And the reference is always, for example, the ticket number. Okay? So for communication, you need certain important IDs, important information there, okay? To communicate within a layer, okay? The claim ticket there for the bag is so that you can pick things up on the other end. But there are also certain numbers. For example, ticket number connects to a bag number. Ticket number also connect to a C number here. Okay, so certain pieces of information might be added there, either to allow communication within the same layer from local side to remote side, or information to allow components across layers on one side to try to relate to each other. Okay. So you see, air travel is a complex system. If any step goes wrong, it could end up being a disaster. Okay, needs to be well structured to make sure also that it's efficient. So there are layers. Okay, each layer implements a particular function. Okay, a particular subservice. Okay, and so there will be some internal actions, but they will also depend on services or functions provided by the neighboring layers. Okay, from the layers below, okay, or they might also need to provide supports to layers above.
All right, so that was an example. Yeah, so Boyu was thinking data structure course, I guess. Yeah, so we do have layers, and it does look like a stack. But the stacking the data structure course actually meant that you put data to the bottom, and when you're taking data out, you actually take it from the top. It's not first in, first out. It's actually last in, first out. Okay, that's the differentiation of data structure stack and the stack, the internet protocol stack that I'm talking about. Good. It's about time to take a break, but I would like to emphasize the video that you just saw. This is related to software engineering. This is also related to how you organize a big company. You see that in a big company, there are lots of people doing their jobs. If there's no structure in a company, right, the communication is all flat, mashed, you can see that it can be very inefficient. And no one is probably aware of whether something is really being taken care of. So you need some sort of structure, okay, in a big company. Air transportation is a big service, big system. Internet also, big service, big system. So we are trying to build a structure out of all these protocols there are on the internet. And the way we structure it is layering, okay, very similar to the air travel. With that said, let's take a break. You guys have 10 minutes. We'll return at 11:20. And those who have not yet typed up your solution for quiz 6, please do. And if you are not exactly satisfied, of course, use the time to try to modify it. And let's take a break now. Yeah, so Hongru was asking a very good question. Yeah, so these are probes for router 2. Yeah, they will be actually picked up by router 2's network layer. There's a protocol called ICMP. And that protocol sees this packet is for router 2, then they would ask router 2 to send a response, unless the network administrator of router 2 turns that function off. Now, all the other packets that are not traceroute probes for router 2 will be treated just like the other packets, okay? And they'll be forwarded by this router 2 to their supposed destination or next hops. Yeah, so this is a little bit, that probing messages are a little bit special when we send data. You know what, Hongru, that is perfectly right. A lot of times we send data, right? And we thought that, hey, the delay is suddenly long. And the packets are coming and not coming and coming and not coming. And so you want to find out what's going on and where the problem is. If you do just ping, you get only the delay and the loss. With trace route, you can potentially see where the bottleneck is and which router is not being stable. So you get to see also where the problem is more likely. So ping and trace route, they are typing during the break, get my... Oh, okay, sorry about that. Okay, so probably I need to get a quieter keyboard. Sorry. Yeah, I think it's coming from me. So you know what? Maybe I can. Okay, sorry about that. Yeah, so yeah, I'll pay attention to that. Probably during the break, I can mute my mic, but sometimes I will forget to turn the mic back on. Sorry about that. So we'll see. Let me see. Maybe I can move my microphone a little bit farther away. That might generate a lower pulse, lower strings pulse. Then if router 3 probe and data differently, this method won't be right. Okay. You know what? I understand your point. The point is probably that if we are sending data, okay, and data are being passed by one of the routers in the middle, but the probes will be treated specially. How do you know the delay or the reachability of the data are identical to how the probes are responding? Yes, you're right. That's why you asked the question in the first place, right? If you get 3 ostriches, that means, hey, that router, something is wrong. But it can be that the router is dead, but usually not. It could be because the responses are turned off by the system admin. So the way you interpret these ostriches is more that the router is alive. Okay, the better way to interpret those messages is that the routers are alive, but they are not responding particularly to the ICMP traceroute probes. In a way that you don't get the exact delay from you to that particular router, but you can still see the readings from other routers that can potentially help you debug where the problem might be. If you interpret the asterisk as the router is dead, of course, it doesn't mean that. Okay? It looks like the asterisks are saying that routers are dead. But no, they actually, that means we don't have the measurement. But that can be the router is dead. That can be also the router is just not responding to that message, to that probe. But the router is still alive, passing data around. Okay? So if this is still not quite clear, Hongru, feel free. Let's take the conversation to Slack. All right. Yeah, thank you, Ming Duo and Zijun for letting me know. Oh, okay, good, very good. Now, let's talk about how we layer these protocols on the internet next.
Hopefully, with the air travel example you see, in large complex systems where we have lots of these pieces, it's really good to have some explicit structure so that it's a little bit easier to identify in case there's a bug, which piece the bug is, and to find out what are the related pieces might be partly to blame as well. So having explicit structure, really good. And you see in the air travel example, we have this layered architecture, layered service model. That's exactly what we're using, okay, to manage, to organize internet's operation. And we call that layered service model also the reference model, because we are referring to these pieces on the internet in layers as well. Okay, so it's our reference model for discussion among the network engineers, okay, which you are becoming one as well. All right. So this way of trying to break a large complex systems into pieces, okay, and to define, okay, the functionality of each piece is also called the modularization. All right. So after defining the functionality of each pieces, after finding out the relationship between the pieces, okay, we implement the individual modules functionality. We also implement the interfaces to communicate from module to module. Okay, so that is called modularization. Okay, this is really common. We see in large software systems. Okay, because it's a lot easier to maintain. It's a lot easier to debug problems. And it's also a lot easier to improve the system, to move a complex system forward. Okay, because you see, the important functionalities are well modularized. So if we need to change the way we implement the functionality, we can just change it. Okay, and that change does not need to propagate through the entire system across the different modules. Okay, so a change, okay, in a layers service, a change within a piece, a change within a module, okay, can be transparent to the other modules. Okay, because the APIs are already well defined. There's minimum communications required. All right, so it's just like this. Here's an example. If we change the gating procedure and we decided that we let the first class passengers to go last, hey, it's not going to change how the pilots communicate with the traffic control, right, in order to find out which runway to take off. So each module more or less independent, and the communication across modules, across layers are minimal. Modularization or layered reference model, layered service model. Sounds nice. Can you think of anything that suggests such a layering is not exactly good?
All right. Suggest one on Ask Us Anything, okay, if you come up with one. Now, let's move on to the next topic. Sorry, I have not yet tell you the entire IP protocol stack. Here's the video for it.
Here's the Internet Protocol stack, and you see here what I'm illustrating. It's in the layered architecture. The layer at the top is the application layer. So these protocols at the application layers are, okay, literally to support the applications. For example, HTTP is supporting the web application. So you do have application processes sitting on the web browser side and another application layer process at the web server side. Okay, and there's a protocol there. For example, a message go out is necessary from the client to request for a web page, right? And that web page will be another message coming back the other way. Well, that's pretty much what HTTP defines, right? So these messages to control when to start sending and which web pages to send. Transport layer, that's one layer down. Okay, the functionality is essentially to allow these application layer protocols to specify, okay, whether these data that I'll be sending through, these data packets I'll be sending through the internet is going to be reliably transferred
or best effort transferred. Okay, so this is to administer data transfer from client to server process or vice versa. Network layer protocols, on the other hand, very special. Yeah, all these packets, oh, by the way, packets, when it arrive at the network layer, it's called another name, datagram. So these packets coming from the source, right, needs to find a way to the destination. You see, at the core of the internet, we do have a mesh of interconnected routers, don't we? A router could have multiple connections to other routers. So each router will need to know, okay, which is the right router to forward next so that the packet will arrive at the destination with the shortest distance possible, right? Because you do want the packets to arrive at the destination as soon as possible. So a good routing protocol is to ensure something like this. So network layer, the protocols there are essentially to handle packets being forwarded and the directions of how these packets being forwarded in the core. Link layer protocol. Okay, so these are very special. They work a little bit like, honestly speaking, the transport layer protocols. Okay, transport layer is to handle data transfer from one process to another. Link layer protocol here also handle data transfer, but it's between one network element to another one network element, one network hardware to another network hardware, or a network entity to another. For example, between two routers directly adjacent to each other, there's just one link. Okay, so this might across several hops at the transport layer, but link layer protocol only handles data transfer in one hop. Okay, so it deals with the data transfer very locally within a link. For example, Ethernet is a link layer technology, a link layer protocol.
All right. And next video is the last for chapter 1. It's called A Day of Life of an Internet Packet. It's about 6 minutes long, but after this video, you will know very well how packets travel through the protocol stacks up and down and from one machine to another machine over the internet. Okay, vertically and horizontally.
With the layered architecture explained, what I'm showing here is the software side of the internet side by side with the hardware of the internet. So where are the hardware in this example? Look, here, and here, and here. So these are end systems. Okay, this one is the source, and this one is the destination. You see that at the end systems, the entire internet protocol stack is implemented and running. Similarly for the other end system. But in the core of the internet, you see the router over here, and this is a very special entity, hardware entity. It's called switch. But to be precise, this is the link layer switch. Its functionality is limited. Okay? Unlike router, this is a network layer device that implements the protocol stack from the lowest up to the network layer. The link layer switch is a more limited device. It implements only from the physical to the link layer. Well, then you see how it gets the name. It's a link layer switch. And if you want to be precise, you can also call these routers the network layer routers. Or sometimes we actually call these routers network layer switches. Okay, so both of these entities are doing switching, but doing the switching at a slightly different level. All right, now walk with me and let's see how the data gets passed down the protocol stack, out of a physical entity, and through the network, reaching the destination. The first step is this. Yeah, one particular user typing things up. So at the application layer, this component generates a message. Yeah, a packet at the application layer is referred to as a message. The application layer component will pass the message down. As the message arrives at the transport layer, a header is being appended in front of the message. Okay, because it's appending, therefore, these additional pieces of information is referred to as the header. H stands for header. And this is a header appended by the transport layer, therefore HT. The whole thing together, this packet, is referred to as the segment. So a packet at the transport layer is called a segment. And you see that this header here is very important. This is to allow the transport layer component at the source side to communicate with the transport layer component at the destination side. Okay, so this is a little bit like at the airport when we're checking our bag. The counter is going to give us back what? The passport, the e-ticket, and what? The baggage claim ticket. Okay, so that baggage claim ticket, that additional information, okay, in order for you to find your bag, is a little bit like the headers. Okay. And now the segment is going to be passed further down to the network layer. And guess what? The network layer component is going to append some more information to it. And that is in the header as well. But this is the header for the network layer, HN. And the whole thing now, the packet here at the network layer is called a datagram. And the whole datagram is going to be passed down further to the link layer. And guess what? The link layer header is going to be appended, and we call a packet at the link layer a frame. So this frame here, now arriving at the physical layer, what physical layer is doing is simply modulating the 0 and 1 bits, okay, onto the physical media. So it's going to go out shortly through the network interface and arriving at the router here. Now I'm skipping the switch here because it's a link layer device. We'll not be able to cover the link layer chapter. So this message is going to arrive here at the router, receive at this physical layer, and the signals gets converted to the digital form. So we restore the original frame back, and that's passed up into the link layer. The link layer at the router is going to examine this header and see if there's any additional function that it needs to perform. When everything is done, guess what? Okay, this header is going to be removed. So only the message with the transport layer header and the network layer header will be passed up to the network layer. You see here, the message is being passed upwards, okay? Because the network layer component of the router still needs to check this, okay, and see if there's something that the network component needs to do at the router. So this is going to be examined, okay, and functionality is performed. Now this part, hey, as this is a router, there's no other layers above. So this is going to be copied over, okay, and stand by there at the outgoing interface. Now before that message go down to the lower layer, the new network layer header is appended. And this one is a datagram. It gets passed down to the link layer header appended. And this is a frame. It goes to the physical layer, bits modulated, traveling the link and reaching the destination. Similarly, the physical layer is going to recover the 0 and bits and give this up to the link layer. This checked by the link layer, and the remaining gets passed up to the network layer. And you see this removed, this part gets passed up to the transport layer. This removed, and this part here gets passed up to the application layer. And here, the destinations processed there at the application layer, finally you see the message coming from the source originally. So this is how a message travels through the protocol stack and the physical infrastructure, and more protocol stack up and down until all the way up to the application layer and the destination.
All right, so the journey of a message through the internet. And hey, congrats! We're done with chapter 1, and we'll break open chapter 2. This video is a little bit long because Polly will break open and tell you the structure of chapter 2, and Polly will also start talking about the applications that we are using on the internet, because chapter 2 is called exactly Application Layer Protocol.
Flow of chapter 2 is this. We'll start by talking about the design principles, particularly how one designs the application layer protocol for data transfer in an application. Second, we'll go over a number of these popular applications as examples, okay, and demonstrating how we exercise these design principles and coming up with the application layer protocol for each of the applications. So HTTP, how it's designed to support web page transfer. FTP, the protocol to support file transfer. And these are the protocols to support email transfer. DNS here is to support transmission of hostname to IP address mapping. So a lot of time when we request data files, we actually give it a hostname. But messages on the internet do not get to the destination by knowing the hostname. They actually get to the destination by knowing the IP address. And therefore, for every messages you send out, we need to translate from the hostname to its IP address. So DNS is an application that we use every day and frequently each day. P2P applications, usually not all of us have experience using these P2P applications, but they are quite popular these days. For example, BitTorrent, for example, Skype, for example, Bitcoin. So the way data are being transferred on P2P applications is quite different, okay, from the more traditional applications such as web email. So in the traditional applications, we do it more client-server way. Someone asking for pages and server returned with pages. In P2P, each of these computers involving the communication, the roles are actually equal. One can be providing services to each other. One can also be requesting services from each other. Okay. There's a certain advantage of transmitting data this way. We'll see when it comes to 2.5. And then multimedia applications. So by multimedia, I actually meant video, okay, transmission of video. You see that video quite different from the content being transferred here. So web, file, emails, these are all text-based. Video is a very different type of content. So if you think about it, video is a stream of picture frames, okay? So the volume of data is by default higher. And these frames need to be streamlined through the network so that they arrive one after another. This is to ensure smooth playback of the video. That's why when we say video transfer, we don't quite say the video transfer. A lot of time we say video streaming, okay? Streaming applications. And because of the nature that these video content, we do have short delay requirement. We do need more bandwidth to transmit higher volume video content. When we talk about multimedia applications like videos, we talk about this, CDN, Content Distribution Network. So this is a network of content servers. Okay, these content servers, usually there are multiple of them, and they are placed here, there on the internet, and hopefully close to the video users, to the video consumers, such that the delay will be short. Such that the segment of network is small, therefore you run into less bottlenecks, therefore the throughput or the bandwidth, effective bandwidth is higher. Okay, so video streaming and this very interesting way of designing a video application using content distribution network. So these will be the key content we talk about in chapter 2. We'll skip this, socket programming using UDP TCP, because in the PAs, the practical assignment or programming assignments, in those videos, you will see how we do this using Golang socket. To make sure that we're in sync, let's inventory some of the popular network applications here. Email, web, nothing more need to be said. They are obviously email and web. Text messaging, Line, WhatsApp, what else? A Google Messenger. And if you guys are watching this from a YouTube live stream, that chat room is a text messaging app. Remote logging. If you downloaded a client to remote logging to the PA server, then you're using a remote logging application or remote logging service. P2P file sharing, the most well-known one, BitTorrent. Okay. Multi-user network games. Okay, so this is a more formal way of calling online games. Okay, so some of these online games are running on desktops, going to the game server somewhere provided by the game company. The client can be nowadays running on smartphones. In fact, probably more games people are playing are mobile games. Okay, so the client is on the mobile platform. And then the multimedia applications. Here we have the streaming stored video, and we have the real-time voice. So this is also called the voice over IP. And we have the real-time video. Okay, well, real-time video conferencing, of course, also comes with audio. Okay, so essentially these three are multimedia applications. The difference between this and these other two is that the video is actually a playback video. So the video is already stored in one of the video content server, and when you request it, it is just playing back the video. But for these are the live video being generated as you guys are having conversation, as we are having conversations. So the delay requirement for live audio video is a little bit higher, more stringent. So what do we have as real-time video conferencing apps? Yeah, Google Me, the one we have standing by here, allowing you guys to call in, is a real-time video conferencing app. So there are other real-time video conferencing apps such as Zoom, Microsoft Teams. What else? Well, Skype. Although transfer audio, it also transfer video. So Skype is also a real-time video conferencing app. So there are many options here. Social networking, hey, Facebook, IG. One can probably come up with others such as Snapchat. Yeah, so there are just increasingly more of these social networking apps. Search, Google Search or Bing. Yeah, each of these is also an application or a network service. Cloud computing, yeah, Amazon AWS, for example, is a cloud service. Now, to support all these applications, the principle is quite straightforward. Essentially, we write programs. There involves at least two parties. One program sits on one of the parties. Particularly, each of the programs sits on each of the end systems involving the communication. Okay, so they will be communicating, sending messages over the internet. So for example, web server program sits on the web server machine. Browser sits on the client machine. And these two programs send messages to each other. Much like this. So we might have a web client here. We might have another web client here. And the web server is down here. And we establish connections like this. So this client's program interact with the server's server program. This client's program interact with the program running on the server as well. Okay, so you see that the server program here needs to be a little bit more powerful, allowing requests from these clients, okay, frequently and potentially simultaneously. So essentially, in order to create these network applications, we design how the messages are exchanged, meaning designing an application layer protocol. Afterwards, we program the softwares. There'll be one part running on one end, the other part running on the other end. So this example here is a client-server application. For P2P, one runs on peer, the other runs on another peer. But in P2P, these two programs usually are identical because they are both peers. Now, what's unique here is this. Applications run only on the end systems. In the network core, these routers, the routers do not run anything particular for a particular application. Okay, so the core devices do not run applications. They do not run specific functions to support individual application. Okay, so applications are strictly on the end systems. So clients, limited devices such as a smartphone, such as a laptop or desktop, are on the edge of the internet. But you see here, servers, more powerful machines, they can be quite expensive. Some of them can be just as expensive as the routers. But these servers are also at the edge of the internet. They are also end systems. Just don't be confused. Okay, so these end systems, there are programs running and exchanging data such that we can perform a specific application or specific service.
All right, so that was an overview of chapter 2. And here comes quiz 7. Okay, so Polly oftentimes like to survey from you guys, okay, what you guys are doing on the internet. Okay, so this is how I get in sync with the rest of the world, rest of the society. So what's nice about teaching, being a professor in a college, is that I do have you guys. Okay, so quiz 7, very straightforward. You just speak from the bottom of your heart, definitely, please. Okay, so Q1, list the top 2 network applications you use on a PC or laptop. Okay, desk, laptop. List 2 frequently used network applications on your smartphone. Oh, more mobile. List top 2 games you play, okay, on either of the platforms. Okay. Good, so this is very straightforward, so I give you 3 minutes. Okay, so speed typing now. Okay, go.
Okay, probably we probably don't need 3 minutes. I see already some teams type up. I guess you have prepared. Um, so Claudia says for Q1, Google Drive. I see. How secure? For VPN, isn't it? Now you need to work on PA2, which is due in Saturday. Q2, IG, definitely. YouTube, yeah. So I think on the smartphones we do audio, video more, visual content, audio content. Good to see you alive, Claudia. And Kevin, let's see. Google Chrome. Yeah, I use Google Chrome like, whenever I'm awake, pretty much. GitHub, cool. Yeah. So I'm thinking moving all the PAs to GitHub. Okay. And then on the smartphone, Messenger, IG. Yeah, Messenger, texting, friends, social network. IG is lots of pictures with the friends as well. So yeah, I see in Kevin's form, it's more social networking on the smartphone. Oh, games. Yeah. I neglected checking Claudia's frequently play games. Genshin Impact. What is that? I see that also in Kevin's answer here. Okay, PUBG. I've heard of that. Genshin Impact. Okay, I'll look it up. Interesting. All right. Oh, Team 15, you have complex answers. I guess each of you have your own. Yeah. Cool. Thank you. Line and Discord, line, YouTube, this. Oh, D-card. I guess it's also a kind of social network, maybe, or a discussion forum. And in terms of game, auto chess. Oh, okay. Oh, you play chess. And you played it on laptop. Good. Go is also a board game. Yeah. Apex. I've heard of that game, but no time to play. Sorry. Cat War. I love that game. Okay, Minecraft. Of course. Okay, Dino. I Dino. Yeah, I suck at that game. Yeah, the dinosaur running jumping game. Good. Yeah, I see Chrome, Discord, Messenger, Netflix, Spotify. Okay, movie, and music, of course. LOL, of course, it's very popular in Asia. And of course, the rest of the world as well. Candy Crush, Fruit Ninja. Yeah, I also love the round-based games because these sort of league fighting combat strategy games usually take more time. I'm never sure of having enough block of time to play role-playing game anymore, to play the strategy game anymore. But in a way, Minecraft is also that, you can stop at some point and then come back to work on it. Definitely. Okay, Minecraft. Interesting. Minecraft. YouTube, Netflix, Google. Yeah. Google Map. Line. Okay, Scott here is very communicative. Yeah, line all the time. Okay, so these games are very, very new to me. All right, so yeah, good to have your input here. Yeah, that's Polly will definitely come back to go over them. Okay. Yeah, League of Runeterra. Yeah, there are lots of these new. Elden Ring. Yeah, it's a popular game also now. Apex is also a popular game, I know. Zenly. I don't know what it is. Okay. Team 6, Ming Duo. maybe you can tell me more. I mean, I can also look it up. Okay. Mo PTT. Okay, so I didn't know Youxiang follows PTT. I thought you guys are more D card. Okay. Anna? Don't play games. I see. So I guess Anna is very outdoory. That's good. Good for you. Spotify Safari? Oh, okay, okay. I guess Shen likes to cycle. Good, good for you. What of tanks? Okay, good. Okay, thank you, thank you. That completes Polly's survey, okay, of the popular apps. And now we move on to the lectures. Okay, so first thing we need to do designing or developing a network app ourselves is, of course, to decide the architecture, the necessary components in the communication. Okay, so this video talks about architectural choices. The first thing we decide designing an application is its structure. There are two major models, client-server and P2P. The third kind here is the hybrid of the two. This is usually for bigger services where part of the service fits better running in client-server model and the other part running in P2P. The client-server model is straightforward. There are two ends. One is server, the other end, the client. The server is one of these powerful machines that's always on, running on permanent IP address so that they are always reachable. Now, given the scale of the internet service today, instead of using just one physical server, we need multiple of these, and they are housed in one of these data centers so that we could serve thousands and perhaps millions of requests at the same time. The clients are you and me. We are lower-end machines and scattered around on the internet, communicating with the servers, requesting services from the servers. Now, unlike the server that are permanently connected, permanently reachable, we're moving around, okay, only intermittently connected. This is because as we move, we might be assigned dynamically a new IP address. So our IP addresses are not permanent. So using one IP might not reach us at another time. So that's why we don't see clients directly communicating with each other. And we see two examples on the left here. So someone in the car might be trying to find the driving direction. So that could be a request to Google Maps server and getting the direction back. Now this could be a student trying to look up PA assignment. So a web request to the web server and the web page or the PDF file returning to the client. In the P2P model, we no longer have the always-on servers. In fact, all these end systems would directly communicate with each other and treat each other equally. So in this P2P world, think of it this way. Everyone is born equal. So the equal peers will request services from each other. They also provide services to each other. So such a characteristic is called self-scalability, because as we join such a P2P service, we ask for services, but we also open up our resources and adding new service capacity. Now, the only drawback of P2P is this. Hey, the peers, they are all intermittently connected, running on dynamic IP addresses. How do we ensure a P2P services is going to stay connected all the time? Yeah, the management of these peers is the complex part. The third model is using a combination of the former two. This is usually used by bigger services where there are service components and some component better run on client server and the other components P2P. Now, Skype is one such service. The component in Skype that's tracking your contacts and where their current IP addresses are is in client server mode. That's called the directory service. Okay, so the central directory server allow you to find the IP addresses of a remote contact. Once you decide to call someone, the calling service runs in P2P mode. That IP address is used by you to make the P2P direct call. Yeah, so you see, client server, P2P, and hybrid. Now you can use both in case your system, your app structure, you want it to be a little bit more complex. Okay. All right. Next, once you have the architecture settled, then you start creating sockets so that your client server or your peer can talk to each other. So let me introduce this thing called socket.
To implement a network application, it's equivalent of allowing process-to-process communication. Okay, so in client-server's case, a client process communicating with the server process. In the P2P case, peer-peer processes. Take note, the server process, remember server is the one that's always on, right? So server process is always started early, since the beginning of the service. Only when the service is started, then you call that the service is available. Okay, and it's always there waiting to be contacted. The client process is the one after being started by the user, initiating communication to the server and getting something back from the server in return. Now in P2P paradigm, the exchange between the peer processes are then a little bit complex. Each peer process will have the client side and the server side implemented. Okay, the difference is that this peer process client side contacts the server side of the other peer and vice versa. But either case, process to process communication. This is how you enable network applications. Now, let's take a step back and review. What is a process? It's a program running on a machine. So in fact, for two processes on the machine, there are occasionally the need to communicate with each other. Okay, this is possible and enabled by this set of API called Inter-Process Communication API. This is defined by every operating systems today, and this should be covered in the operating system course. Now, in case you don't have this, you might want to look it up a little bit, ep6. Now, in this course, we talk about process communicating with another process that are on different hosts. So two processes exchanging messages on different machines. How do we do this? We do have another set of APIs defined called the socket API that allow us to do this. If you call the socket API, a socket is created and associated to a process. And that's when the process can begin sending, receiving messages through the internet. Now, think of a socket as if there's a door. On one end of the door, the sending process pushes messages out. The other end of the door, we have the transport infrastructure. So let me explain with the picture here. Sending process here. Sending process pushes the message down, reaching the transport infrastructure. So the infrastructure here will move the packet further through the internet and come to the receiving end of the infrastructure. From here, messages go through the receiving socket and reaching the receiving process. And you see, process-to-process communication enabled by the socket API. Now, let me draw your attention here. From this line and above, this is application layer. Everything running here needs to be controlled and defined by the application developer, application designer. So it includes the functionality of the sending receiving processes as well as the kind of socket we want here and here. Hey, why is it challenging? Because the transport infrastructure, there are actually multiple type of services being provided. So in order to call the socket API creating a socket, one need to know which transport protocol to choose. This depends very much on the kind of applications you're designing. You might also define additional parameters so that a process is correctly associated with the socket. One very important parameter to define before creating a socket is called the port number. So the port number, you can think of it as a unique identifier for a process running on a machine. So keep this in mind. And now let's take one step back and think about why we need a port number. All right. So let's see how we uniquely identify a process running on the internet. Well, first is, of course, try to find the machine the process is running on first. How do we identify a machine on the internet? Yeah, we do have IP address. You guys should all have heard about IP address. It's a 32-bit long number. With this IP address, we identify a machine. But the question here is, does the IP address allow us to identify a process running on the machine? Having just the IP address, is it sufficient already? I know what you're thinking. You're probably thinking, no, not quite. If there are multiple processes running on the machine,
then you cannot see exactly which process, right, we're looking for with just the IP address. Therefore, in order to identify uniquely a process running a machine, we need something extra, the port number. So for a process running on the internet, in order to uniquely identify it, we need the IP address plus the port number. Okay. So a few example port numbers. For example, HTTP server, this is to support World Wide Web. It typically runs on port 80. So the socket connecting to HTTP server is on port 80. For mail server, port 25. It's a very common practice on the internet. For these very well-known services, we use a fixed port number so that it's easier for the programmers to remember. So that is also saying to send a web request, which is a HTTP request, to a server, gaia.cs.umass.edu. We send that message to here, or that socket is defined by this IP address and this port number. So this is the IP address of the web server, and this is the port number of the server process running there. All right, so define the architecture components in the communication and create a socket. As you heard, configuring the socket is not that straightforward. You need to know what the transport layer service you want to use. And having the socket is one thing, right? Eventually you need to send messages around. So next Wednesday, I'll start by talking about, you need to start sending messages. Okay, what are the tricks? Okay, defining the messages. And how you choose the transport layer protocol, it actually depends on this thing called QoS, quality of service, and I'll explain on Wednesday. All right, with that said, we'll call it a day because the next videos are all longer than 3 minutes. If you have other questions, feel free to type them up. If you have not yet completed W3 Quiz 7, please do so. And that's all. And for your information, starting from 12:10 to 1 o'clock, this is office hour, Pollys in office, you can use the Google Meet channel to just call in, okay, if you want to do verbal Q&A. So that's all. See you next week. Okay, go get lunch. Polly needs to go get lunch as well. Oh, good point, Caffrey. Guys, no, don't go yet. Wait. You know what? Caffrey is right. Next Wednesday is the Teacher's Day, so teacher gets a day off. Well, because of that, you guys get a day off as well. So, Anna, you're right. Wednesday, no class. Yay! So I see you Thursday. Okay, Thursday morning. Good. Thank you, Caffrey. Thank you, Anna. Okay, and Vincent, I see you next week. Okay, bye. Go. Enjoy the weekend. If you don't have classes on Friday or Thursday afternoon. Yeah, see you. Au revoir. Yeah, so excuse Polly sometimes speaking with a British accent because I lived in Europe for a while and I somehow pick up the British accent. Okay, so yeah. And the last couple videos, I do have the mic too close. I realized also today. Okay, Belen, you were still thinking about quiz 6. I see. Yeah, I think maybe, yeah, you can probably think of it that way because the delay difference is just so small. Chances high that they are so close, the difference is negligible. Yeah, so you argue and justify your solution. Very good. Can we call in? Sure. 志源, feel free. But if you, because I'm still streaming, yeah, so I'll be closing the stream in a minute. So after that, feel free to join. That way you don't get streamed out also to the rest of the world. Okay. And I hope that you don't mind that we stream the lectures globally, because I feel that it's helpful. I feel that it's helpful. Okay. Okay, good, Belen. Good point. And I see Claudia. So let me end the stream. Okay. Okay, bye. Bye. Let me end the stream. 1 second, Claudia.